In Essential Task 8.3, we are going to describe the function and various disorders related to the key neurotransmitters. This essential task, I think, works the best horizontally. We're going to introduce the two different categorizations of neurotransmitters and then talk about 7 specific neurotransmitters left to right horizontally at the bottom. I will return, though, to the task text, allow you to copy down, in this case, the entirety of the task text in yellow. There are 2 different types of neurotransmitters in our body. There are neurotransmitters that are classified as excitatory or inhibitory. Each type of neurotransmitter has a different overall function in regards to action potentials. As we denoted in Essential Task 8.2, action potential is the term that we use for the brief electrical charge that travels that way across the neuron once that neuron has been stimulated at its receptor sites beyond its threshold of excitation. Assuming that neurotransmitter is classified as excitatory, that neurotransmitter is going to produce and cause more action potentials. So when we talk about neurons communicating with one another, and we assume that neurons are going to create essentially a domino-like effect, where one neuron is going to trigger another neuron, which is going to trigger another, we're going to assume that those neurotransmitters are classified as excitatory. We're not going to go through and classify every single neurotransmitter into each of these categories. We're only going to categorize a couple of them because sometimes neurotransmitters can work a little bit like both depending on the circumstances and where in the brain each of those neurotransmitters are active. But just for the framework of what we're talking about, if a neurotransmitter is classified as excitatory, it's going to produce more action potentials. There are some neurotransmitters, though, that are inhibitory, meaning when they are active in the synapse, they actually do the opposite. They inhibit or slow down or stop action for potentials from occurring. Those would be the types of neurotransmitters which might be active when you're dozing off in class, or when you're about to go home and take a nap, or when you're drifting off close to sleep. When I look at the word excitatory, it reminds me of the word excite. When you're thinking about getting excited, or you think about the phrase excites action potential. And then alternatively, the word inhibit means to stop. Again, inhibitory neurotransmitters slow down or stop action potentials from occurring. As I alluded to when we first introduced this essential task, there are 7 different types of neurotransmitters that we need to know. The thing with neurotransmitters is that most of these neurotransmitters have multiple functions and that they influence several aspects of our behavior. So I've tried to identify key functions, things that are the primary functions and the functions that are most likely to appear on the AP exam. First neurotransmitter is serotonin. The primary function of serotonin is it is considered a mood-regulating neurotransmitter. When individuals have an abundance of serotonin in their synapses, it's likely going to be correlated with an elevated mood, and then low levels might be correlated either with a depressed mood or actual clinical diagnosis of depression, whether that's major depressive disorder or persistent depressive disorder, or even, in some cases, bipolar disorder, particularly the depression aspect of bipolar disorder. These are important functions because, as we'll talk about in next unit, one of the pharmaceutical drugs, or one of the brands of pharmaceutical drugs that is designed to treat forms of depression like major depressive disorder, are designed to block the reuptake phase in neural communication, which means when serotonin is active in the synapses of an individual who's taking Prozac acts almost like a gate or a wall, making it so that the serotonin cannot be reabsorbed back into the terminal of the sending neuron, the presynaptic neuron, and it locks serotonin in the synapses of those individuals longer than would be natural. Essentially, drugs like Prozac try to amplify serotonin that is already active in the brain, and instead of adding more or mimicking serotonin, it actually just tries to harness the serotonin that's there and amplify its overall effects. So when we look at serotonin, the key function is to always think of mood as a mnemonic. When I look at the name, it kind of looks like the name Sir Rotten. And I use that mnemonic because the phrase or the term rotten mood is pretty common culturally. And if you always see that word rotten in the middle and you think of rotten mood, if the number one thing that you recall with serotonin is that it has to do with mood, then you'll probably be able to differentiate this term from the other neurotransmitters. It will also help connect to mood disorders, which we'll talk about in a later unit. The second key neurotransmitter is called acetylcholine. Acetylcholine has 2 primary functions. So I typically try to limit it just to one, but acetylcholine definitely has 2 key functions, and it's conceivable that the College Board chooses which of these 2 because they're quite interchangeable. But for our purposes, the 2 key functions of acetylcholine is that acetylcholine is the neurotransmitter that enables muscle movements, specifically via motor neurons. Earlier in this essential task, or rather in this unit, we talked about motor neurons enabling muscle movement, such as turning the wheel if you're driving, lifting up a pen. Well, to be more specific about that process, acetylcholine is the neurotransmitter active in the synapses of motor neurons that actually enable that muscle movement. Acetylcholine is also linked to memory. There's a very strong correlation between a significant decrease in activity with acetylcholine and Alzheimer's disease. If those of you who have familiarity with Alzheimer's disease, you probably readily know that one of the significant symptoms of Alzheimer's disease is a massive deterioration in memory, particularly in the formation of new memories, but also some long-term memory deterioration as well. So there's a really strong link between acetylcholine and Alzheimer's. And as you might imagine, low levels of acetylcholine would inhibit movement and obviously, as we just alluded to, memory. It is actually acetylcholine that the venom of a black widow spider, or the poison of a black widow spider rather, affects, making it so that acetylcholine cannot function properly. If you're familiar with what would happen if you were bitten by a black widow spider, you would become paralyzed and then, assuming you're untreated, soon die after. It is because acetylcholine, as we're just talking about, enables muscle movement. As a mnemonic, this one I think is actually more effective than you might anticipate because it's kind of an interesting one. When I look at the word acetylcholine, if I go down the line, ACE, I see ACE. The TY, I know it doesn't say the, but at least begins with T. I see the HOL in the middle and then the INE. And to me, if I look at that, it almost looks like the phrase ace the hole in one. And when I say that phrase, ace the hole in one, I always think of golf because in order to get a hole in one in golf, two things need to happen. One, you need to be able to move. Acetylcholine enables muscle movement. And two, you probably need to know what the course looks like or the hole looks like beforehand. So you're going to need memory of the course. So the two primary functions of acetylcholine, movement and memory, connect to the ACE, the hole in one mnemonic. Additionally, always connect the A in acetylcholine and the A in Alzheimer's. That is a question that you'll see on the multiple choice. Third neurotransmitter is dopamine. Dopamine is active in the brain's reward system pathways, meaning, and this varies person to person, when we do something that we consider rewarding, it's not inconceivable that there's quite a lot of dopamine active in our synapses. And for example, that varies. I might find it very rewarding to play a card game and win. You might find it very rewarding to find a great deal shopping online. Another person might find it really rewarding to eat junk food. A fourth person might find it really rewarding to win at gambling. That pleasure reward system, that rush of dopamine that we experience, is that euphoria that we connect to those types of behaviors. High levels of dopamine seem to be connected to schizophrenia, a psychological disorder we'll talk about in next unit, while low levels seem to be connected with Parkinson's disease. Although it's not the primary function, dopamine does have a connection to some elements of our movement. One of the symptoms of Parkinson's disease you might have familiarity with are the tremors, sort of the shaking that you might consider. Well, that could be related to the lower levels of dopamine. This is a preview of something later this unit, but if you were to, and you definitely should never do this, but if somebody were to take cocaine, not you, somebody else, what cocaine does is it actually blocks the ability of dopamine to get reabsorbed through the reuptake process, similar to how Prozac does this to serotonin to treat mood disorders. So when somebody is using cocaine, what they're really doing is amplifying the dopamine already in their brain and just shooting it through the roof because that dopamine can't be reabsorbed back into the neuron that sent it. So it gets locked in the synapse way longer than it typically should, producing that euphoric feeling that somebody who, in this case, is using cocaine would experience. As a mnemonic, when I look at the word dopamine, I hear that word dope. Dope is a synonym for cocaine, but also just that word dope. I mean, even if we're not talking about it in the context of drugs, dopamine is amongst all of the neurotransmitters, the one that's probably, as you might anticipate, the most rewarding, the one that you want the most. Not that you don't want the other ones, and quite frankly, you need all of them to function, but dopamine just has that really innate connection to pleasure and rewards. It is dopamine that might explain to a certain degree some behaviors related to addiction. You know, that brain chemistry with that dopamine rush while somebody is gambling or doing something in that manner, that could be a connection that we'll talk about at a later point this year. The fourth neurotransmitter is norepinephrine. Norepinephrine is active in order to help us with alertness and arousal. So assuming you're not sleeping right now, assuming you have some degree of alertness, there is definitely activity in your synapses where norepinephrine is active, keeping you alert and focused. In a fight or flight response, when our body has to determine whether or not the threat is worthy of fighting or running away, we would see activity in our synapses with tons of norepinephrine. It isn't the only reason why the fight or flight response kicks in, but it is one of the reasons why we might see an increased heart rate and blood pressure during those moments. Obviously, there are other things that you've probably heard of, like adrenaline, which we even talked about earlier this year, which also connects to the fight or flight response. More on the fight or flight response later when we talk about the sympathetic nervous system and the parasympathetic nervous system. But nevertheless, norepinephrine influences alertness and arousal. It's a little bit of a silly mnemonic, but I look at the word pine in the middle and I think about what would happen if a giant pine tree fell over. You'd get really alert really fast. You'd probably jump out of your chair. So whenever I see that word pine in the middle, I always think about a tree falling over and triggering a ton of alertness. The fifth neurotransmitter is called endorphins. It's not inconceivable that you've heard this one too. Endorphins very simply have the primary function of working as your body's innate pain stress maintenance system. Drugs like morphine and opiates actually try to mimic the chemical structure of endorphins. So although they themselves are not endorphins, your brain is in many ways tricked when you take an opiate like heroin or something like morphine into thinking that it is an endorphin. So the effects of those drugs work because they mimic endorphins in the synapses. More on that later, but a little bit of a preview. Anyone familiar with what's called the runner's high? It's this euphoric feeling that a lot of people get while exercising, particularly long-term exercise, running, biking, skiing, things along those lines. Because when you do those really long-term exercises, your body is going to put strain on its muscles, and as a result, your body is going to use endorphins in order to maintain that pain relief. And as a result, you might actually experience this euphoric feeling called a runner's high. When I look at the word endorphins, I think of racing dolphins. That's just what I always picture. And if a bunch of dolphins have to race, particularly long distance, let's like cross-country racing, perhaps they have endorphins active in order to alleviate some of that pain and strain on their muscles. There are only two neurotransmitters remaining. These ones, we're going to kind of simplify what they do, at least relative to the previous. We talked about the classification of excitatory neurotransmitters at the beginning of this essential task, meaning these are the neurotransmitters that have the primary role of just continuing action potentials, just making neurons continually fire and experience neural impulses. Well, the most common excitatory neurotransmitter that's active in your body is called glutamate. And we're just going to summarize it as having some role in most basic cognitive functioning. So if you're thinking, you're writing a paper, you're doing an essay, you're making a project, you're thinking about your day, planning something out, all of the neural activity that's going on in your brain, let's just say the majority of it is going to be influenced by activity of glutamate. Glutamate will be triggering those action potentials, allowing you to process things, allowing you to think, allowing you to plan things and decide things. You know, if we did a brain scan or really tried to concretely pinpoint the activity in your brain during a test, there would be tons of glutamate active in your synapses. When I look at the name glutamate, it almost sounds like the phrase glue to make. And I always think if you're making an exciting project, one, you'd have a lot of glutamate active in your synapses because you have to plan out the project. But two, hopefully it's really exciting. That way you can connect the word exciting to excitatory. The last one is what we call GABA. GABA is just going to do the complete opposite of glutamate. It is just the complete 180. GABA is a neurotransmitter that can help relax you. It's the most common inhibitory neurotransmitter in your body. Again, inhibitory neurotransmitters have the job of slowing down brain activity or slowing down neural activity, often brain activity. It isn't the only reason why one might fall asleep. There's a hormone called melatonin, which we'll talk about later, that has a bigger connection to regulating your overall sleep cycle, the actual 24-hour or so cycle that you live with. But GABA does a good job of relaxing you during, for example, the afternoon when you're kind of dozing off at home, or maybe you're in a class and you're dozing off. GABA does a great job of just easing neural impulses, slowing down action potentials, and it can get to the point of dozing off. Individuals with insomnia, which we'll talk about later in this unit, but insomnia is a disorder which has a primary symptom of being unable to fall asleep. Individuals with low levels of GABA seem to have at least a higher likelihood of exhibiting the symptoms of insomnia. There are actually some drugs that can mimic GABA so that individuals who might have low levels of GABA active in their synapses can take these pills and the drug can mimic the effects of GABA, hopefully allowing that individual to fall asleep. As a mnemonic, I look at the word GABA and I think of the phrase makes you want to GABA a pillow, makes you want to go to sleep. If you simply connect GABA with falling asleep or relaxing, that would be a sufficient way of understanding this neurotransmitter.